Hello, can you hear me?
Oh, yeah, we hear you loud and clear.
Yeah, great. So, so good afternoon. So I'm gonna record this lecture and I'm gonna post it as well. So let's start. Yeah. So I think you should have received my email about posting the syllabus, which I call it chapter 0 or syllabus, and also chapter 1 in iLearn. So if you can't access them, please email me or let me know. So my name is Muhammad Mahmoud. I'm the instructor of 2850. As you know, we're going to meet in every Tuesday and Thursday from 4:30 to 5:45 in Brunner Hall, 119. So here, this is the syllabus. I'm going to go through it quickly, and then after that, I will start chapter 1. So as you know, this course is the purpose of this course is to teach electric circuits. So here I put some stuff we are going to teach here. This is mainly is about you need to learn what is electric circuit, what are the elements or the components we are using, how can you do analysis in case of DC or AC circuits. So that's what you will see in this course. This is the textbook we are going to use, Introduction to Electric Circuits. I think the slides, if you want to buy it, that's okay. But I think for learning this course, the slides are very detailed. And by the way, I'm not, I can't claim credit for these slides. I have to be honest. I took the slides of Dr. Redman. I am doing just very little modification because this is the first time I teach this course. So here I'm writing here as outcome. So after you finish this course, what should you learn? So I'm not going to spend some time because that's what you are going to learn here in this course anyway. These are the topics we are covering in this course. It's about electrical quantities, units, introduction to DC circuits, and so on. For attendance is required. So for sure today I'm not going to take the attendance because the school is already closed. But during the normal or working days, or when the school opens, I will take the attendance for grading. So here, similar to I think most of the professor, this is a standard grading scale. That's what I'm going to use. If you get more than 90%, you are going to get A in this course. Between 80 and less than 90, so this is B. C between 70 and less than 80. Grade G is between 60 and less than 70. Less than 70 until or greater than 60, less than 60 failure. So, and this is the way I'm going to grade this course. Number one, we have quizzes, we have tests, we have final exams. So there will be several quizzes in this course. They are going to make 30% or 30 points. There will be also several tests in this course. There will be 30 points. The final exam will be 40%, and it will be comprehensive. So makeup tests or quizzes will be only allowed in very exceptional cases. So this is the content of this course. I have already posted chapter 1. I'm gonna post the chapter 1 is very small one. Same thing for chapter 2 and I think 3. So these very short chapters. So I think I'm gonna post the chapter. So when you see here we have 12 chapters, you think this very big course, but actually these chapters are small. Most of them are small chapters. Anyway, so I'm gonna post chapter 2 maybe today or tomorrow. I have already posted chapter 1. Here I give you some information about the disability accommodation about resources, other resources, about tutoring, health and wellness. So I'm going to leave this part for you to read. So now I'm going to start chapter 1. Let me see here. Yeah, so here's chapter 1 is about electric circuit variables. So first, in the very beginning here, I define what we mean by electric circuit. What this means? It means interconnection of electric component. That's it, or electrical elements. And in chapter 2, I'm going to explain what I mean by electrical elements. Okay, so we have electrical elements. We have to connect these elements together in a closed path. Okay, it has to be closed path so that electric current may flow continuously. Okay, so because this is PowerPoint doesn't allow me to write on the screen, so I'm going to use sorry, this is PDF does not allow me, so that's why I'm going to go to PowerPoint. So for example, I'm going to give you very simple circuit here to understand what I mean. If I put here a battery, for example, and you have here some resistors here, one here, and for now I'm going to use just simple resistors. Okay, so the current now it has to be closed. So the current will come here, and then the current will be divided this way, and then you are going to come back to here. That's what I mean by a circuit. Okay, it has to be, we have some elements, we need to connect these elements together to allow the current to flow. Okay, anyway, that's too simple. And one more thing, when the current flows this way, actually what we do, we transfer electrical energy, so that if you have here, for example, if you, I'm sorry. So actually what happens if you have, for example, a battery here, you put a resistor here, and then you put a lamp here or a bulb. Okay. So when the current flows this way, so you're going to have light here. So actually what happens here, you converted the electrical energy generated by the chemical reactions here, you converted it into light, or you can convert it to heat. Or if you put a motor here, so you convert the electrical energy to a motion, to mechanical energy. Okay. In order to generate electricity, the very popular ways is either using batteries, and in batteries, we generate electricity by chemical reactions, or you can use generators. Okay, in generators, you convert the mechanical energy into electrical energy. Anyway, let's go back to the slides here. Okay, so, and then after that, here in this chapter, I'm going to focus on some variables. We use them. Okay, so it's more like I'm going to make some definitions. Okay, so the first thing here is electric charge. That's, we use Q, okay, lowercase or uppercase. Electrical current, we use I. Voltage, we use V. Power, we use P. Energy, we use W. Okay, so we need to make, because these are variables in every circuits, so we are going to define them in this chapter. By the way, usually it's like a convention. Usually we use this uppercase when it is constant, when it does not depend on time or change with time, when it is uniform. When it changes with time, usually we use the lower case. So here in this chapter, these are the problems in the textbook. This is a homework. I forgot to tell you, I'm going to give you homework in every chapter, and this homework will not be collected or graded. Is that okay? I will give you solution to this homework. However, I promise you, or that's actually what I will do, exams, quizzes, everything will be similar very close, maybe I do just a very minor change to the homework question and also to the examples in the slides. Is that okay? So all what I need from you to do very well in this course is I want you to pay attention. If you need any help, just let me know. And also, I want you to understand the examples I'm going to teach and also the homework problems. Okay, so I'm going to say it again just to make sure you already received it. So for homework, I will give you homework in every chapter, but I'm not going to collect or grade them. This only for you, but exams will be very similar to the examples here in the homework and the example I'm going to teach in the slides. Okay. The second thing here I want, so this chapter is actually, as you see, as I said, I'm gonna make just definition for these variables. That's it. This is very small chapter. The second thing here about the units you are using. You know, there is a very, it's like a widely used or standard unit. We call it as the International System of Unit, or SI units. Okay, so in SI units we have seven basic or fundamental units. Any other units are actually derived from these ones. So we use here for length we use meter. For mass we use kilogram. For time we use second. For current, electrical current, we use ampere. For temperature we use Kelvin. For amount of substance we use mole. And also for light we use candela. So also here I want you to understand what is the difference between quantity and units. Okay, there is a difference. So length or mass, these are quantities, but when I say meter or kilogram, these are the units used to measure these quantities. Okay, so don't be confused between quantities and units. One of the things is also the prefixes we are using. Okay, I think you should be familiar with them. I will explain very quickly, but you should know what are these. For example, here sometimes we use tera. Tera is actually 10 to the power 12, giga 10 to the power 9, mega 10 to the power 6, kilo 10 to the power 3, centi 10 to the power of -2, milli 10 to the minus 3, micro 10 to the power of -6, nano -9, pico -12, femto -15. Okay, is that okay? So maybe I should not teach these very simple things, but I'm gonna just remind you of how we use them. For example, if I say 3 kilohertz, okay, so all what you can do, any kilo, I can remove it and I can multiply it by 10 to the power 3. Okay, same thing when I say 3 megahertz. So any mega here, I can remove it or by multiply 10 to the power 6 and so on. Okay, also you can do the opposite. For example, I have here 3000. So 3000 is actually 3 times 10 to the power 3. Here 3000 hertz. This one also hertz. And then I can replace 10 to the power 3 by kilo. Is that okay? Same thing if it is 3 times 10 to the power of -3, okay, hertz. So 10, this I can remove it with milli, okay, and so on. So you need to know how can you convert from number to prefix, okay, and also how can you do the opposite as well, okay. So I just did I think this should be easy. If you need any help, just let me know, but this should be very easy. But these are the prefixes we are going to use, the standard ones. You need to know them, okay? Tera, giga, mega, kilo, okay? So let's start. As I told you here in this chapter, I'm gonna make definitions, okay? I'm gonna define what we mean by electrical charge, current, voltage, power, energy, okay? So let's start with the first one, electric charge, okay? And for this one, we use Q. So there are two definitions here, one from the textbook, one from other sources. maybe I like the second one more. So let's see what we mean by electric charge. So electric charge represents the concept that explains the strong electric force that exists between particles. Okay, so we noticed between particles there is a force. We call it electrical force. Okay, and in order to understand or explain this concept, the reason for this force, we use electrical charges. Okay, so we have charges, and because of these charges, we have forces, electric forces. Okay, also, we have the charge, very small charge, electron is a very small, has a very small charge. It is negative charge. And also we have proton has a positive charge. Okay, and it is very small charge. Also, you may know, or you may know from previous courses, that the magnitude of these two charges are the same. So as a charge, as a magnitude, they are equal. So the charge of one proton is equal to the charge of one electron. Okay. However, they have different sign, because the proton is positive, electron is negative. So they are equal, but you need to multiply by negative here because they have different sign. And then after that, so here electric charge, what unit, okay, what unit we are using here to measure electric charge? This unit is called C, or coulomb. So coulomb here, this is the unit we use it to measure the electrical charge. This is the unit used here. Okay, and what I'm gonna define this unit in terms of number of electrons. So this way. So one coulomb is actually equal to 6.24 times 10 to the power 18. Okay, QB or QE, because I told you they are the same as amount. So that means if you have 6.24 times 10 to the power 18 electrons, this is gonna make only one coulomb. Okay. In other words, so if one coulomb equal this amount of electron or proton, that means one proton or one electron, it's the same as I told you, but just one is positive, one is negative, but as a magnitude they are the same. Okay, that means one proton is actually 1 over this one. Okay, that means 1 over this one coulomb. So I just want to show you how small is the proton, or how big is the coulomb comparing to the proton. Okay, so that means one proton or one electron is actually 1.6 times 10 to the power of minus 19 coulomb. Okay, any question here? So this is one of constant values. So I don't want you to remember them. So I think if you need such numbers, I will give them to you. Okay, any question here? So now I want to move to the second variable we have, electrical current. Okay, I think all of you should be familiar with the term electrical current. Okay, so this is the definition of electric current. Electric current is a measure of the flow of moving charges, either electron or protons, moving charges, or the time rate of a change of a charge. Okay. So it measures the flow of a charge. So the higher the current, that means we have more flow of moving charges. Okay, so electricity or electric current, very simple way to define it, just moving charges. So okay, so when charges moves, they make electrical current. Okay, so here I wanna get a relation, mathematical relation between Q and I. I told you here I is the current, and again upper or lower case should not bother you. It should not bother you, upper or lower case. But usually we are going to use the upper case for uniform or constant current, and use the other one when time dependent current. Okay, same thing for Q. Okay, So, for example, let's see. So let's explain more about the relation between Q, charges, and current, okay, and get a relation, mathematical relation between them, and then I will give you a number of examples to just to apply. So I will give you several examples here to apply this relation. So let's do it. So here, yeah. So here, as you see here, if the charges are moving this way, as you see here, so we have Q and we have dq, okay? So Q is actually the amount of charges accumulated to the right of cross AA. So all the amount of charges accumulated here to the right here, that is Q, okay? dq, you know from integration and differentiation, dq means the amount of the change happened in Q. So the amount of charge passing through A during the time dt. Okay. So here again, so Q means the total amount of charge to the right here. dq is actually during the time t dt, and actually, as you see here, because the current is actually the rate of change of Q. Okay. So the charges of the amount of the changes, we can explain it in a different way. We can say dq is actually the changes of the amount of charges to the right during time tt. So what it changes happen to the Q. So Q is actually the total charges here. Okay. From here, we can create an relation or equation between current and between Q. So actually, the current I is actually dq to dt. Okay. You know this d is differentiation. Okay, the rate of change, the time rate of change of Q. Okay. And because Q and I time dependent, so we're not going to write I and Q this way. We're going to make it like a function in time, I of t and Q of t. So this is a very important relation. You should know this relation. So given, and that's what you will see in the next examples. If I give you Q of t, okay, and remember, Q is the total amount of charge here to the right, okay? So if I give you Q of t, which means the total amount of charge here at the right here at time t, okay? All what you have to do, you have to use calculus. You have to use the calculus to differentiate it to get the time. So we have several examples. In this example, using this equation, I give you Q, okay, and then you can, using Q, you can get I using this relation, as you will see shortly, okay. Also, sometimes I give you I and I want you to calculate Q. That's why we're gonna have another relation right now, okay. So I'm gonna use this relation here. If you have Q and you want to get I, okay, so you are gonna use this one. Now, you know, the relation between differentiation and integration, okay, is this way, okay. So if you have I is the differentiation of Q, it means Q is the integration of I dt, okay. So this is from calculus, okay. So this should be, so this one means this one means this one, okay. But what I want to do here is I want to get Q in function or in relation to I. Just in case I give you I in the example, you have to use this formula to get Q. Okay. Again, so now we're gonna have two formulas. This is one formula here, as you see here. I give you Q, and then you can using if Q is given, you can get I using this one. Then I'm gonna give you this formula here. Given I, you need to calculate Q. Okay. So you can use this one, but I'm gonna break or I'm gonna do some changes here for this one. So this is what this means. It means here Q here is the total charges here to the right here at time t is actually equals the integration of from minus infinity, okay. For sure there is no time can't be minus infinity, so we start from 0. So minus infinity until time t, okay. For I it dt, Okay. So now you know, from calculus, if you have from minus infinity to t, I can have something in the middle here. I'm going to call it t0, which is the initial. So assuming this is the initial time, t0. Okay. So here I'm going to say, I'm going to just, this is very simple. This is from calculus. So if you have here the limits of the integration from negative infinity to t, we can put something in the middle here. I'm going to call it t0. So starting from minus infinity to t0, and then from t0 until t. Is that okay? I want to break it down this way. Okay. And then after that, the first part here, I'm going to call it q at time t0. Okay. So this, which is the integration from negative infinity until t0, time t0. Okay. And then this is the last formula. I think this is one very useful. We are going to use it all the time. So here I can say the charge at time t, or the total charge at time t, equal the total charge, the initial total charge at time t0, okay, plus the integration from t0 until t, okay. So this is the initial one. It should be given in the question. You need to calculate it, whatever, okay. So again, maybe I'm going to go through it again quickly. So from here, we know current is actually the differentiation or the time rate of change of Q this way. And then once you have this relation, you can, from calculus, this differentiation can be integration this way, okay? What I want to do here, I want to get Q. If I have I, how can I get Q? That's why I got this formula. Okay, if you want to use formula, if you want to use this formula, it's okay. But I want to get something like that, so that I have here the initial Q. Okay, and then after that, if I have here starting from t0 to t, I can calculate this one. Any question? You will see right now in examples how can we use these formulas here. Any question about these ones here? How we made it? I think examples will be much better. Okay, but again, just to make it simple, I is actually the amount or rate of change of a charge. That means if and this is the definition of flow. You know, flow means it's the same thing for water. If you have a pipe of water and you have like a big flow, what it means? It means you have too much water in a short period of time. It's exactly the same thing. If the current is high, if you have high current, that means we too many charges moved in a small time. This is the same thing here, because you remember, if there is no moving charges, there is no current. Very simple. No moving charges, no current, okay? Because current is actually moving of charge. Anyway, so I'm going to show now using this. So to make it very simple, now we have two formulas here. The first formula is this one here. If we have Q of t given to you and you want to calculate I, you can use this one. The other one here is this one here, especially the last one here, which is the initial value of Q. Okay, remember Q is the total charge here. So this is at time t0, which is the initial time, and then the integration from t0 to t for this one, okay, for I. So if I is given, usually you're going to use this one to calculate Q of t. Let's see. Yeah, so here I just repeat this part here and just make some definitions here to just make sure you understand what's going on here. So when I say this one here, the integration from minus infinity to t, I dt, okay? So what this means? It means, which is this part actually, okay? So this one or this one. So this means the total charge to the right here at time t. How much charge we had here at the right? Yeah. So represent is the total charge crossing the area from time negative infinity to t, okay? Also for this one, it's the same thing, but this one from negative infinity until t0. So they represent the total charge crossing the area from negative infinity to t0. Okay. This one here is actually represents the total charge crossing the area from time t0 until t. One more thing here, if the current is constant current, in this case, Q equal IT. So here there is no, we don't use differentiation here. If there is no if it is constant. So if it is constant, if you have a constant flow of current, it's constant flow. So at any time, all what you have to do is Q, and you can notice here we used uppercase here. So Q, this is the relation in case of constant current. So if I please pay attention here. If I tell you in the question, and I think this is the first example, if I tell you in the question, the current is constant or the current is uniform. So in this case, you can just simply use this one, okay? So the amount of charge here equal to the I, because I is constant, times T, okay? Anyway, so now I want to come to the definition. We already, I want to come to the unit of time of current. We already know that from this equation, very simple here, current is actually charge over time, okay? And the charge is not Q, or the amount of charges is actually used Coulomb. So it's Coulomb divided by second, okay? Yeah, so here actually Q equal I times T, or I is actually Q, or which is Coulomb per second. So this is the unit of the current, Coulomb per second. But actually we didn't use Coulomb per second. We didn't use it this way. We actually, our Coulomb per second, we call it ampere. I think you are familiar with the word ampere. So ampere here is actually equal to how many charge, or Coulomb per second, okay? But we use ampere. This is the unit we use to measure current, okay? So again, if you want to understand it, it means 1 ampere means 1 Coulomb moved in 1 second, okay? So 1 Coulomb moved, when 1 Coulomb moved to 1 second, that's 1 ampere, okay? Anyway, so before I give you examples, I want to talk to you about current. Current has magnitude, okay? And the higher the magnitude, that means we have more flow, or we have more charges moving, more charges, okay? So it has a magnitude. Also, it has a direction, okay? And it can be positive or negative, depends on the direction, okay? So here, you know, positive or negative here means direction, okay? So like when you have velocity is positive or negative, it depends on the direction, okay? So anyway, so here I'm telling you for current I is a variable. It has a sign, okay? This sign depends on 3 things, as you will see right now here, as in this example here. It's actually the actual direction of moving charges. So the sign depends on 3 things. Number 1, actual direction. Where is the direction of moving charges? Number 2, the type of the moving charges, that electron or protons, okay? Number 3, the direction chosen. This is your choice. So I can assume the current is moving this way, okay? And then when I calculate the time, if it is negative, that means it is the other way, okay? As you will see right now, okay? So here, for example, let's have this example to understand it better. Look here, we have here positive charges moving this way, okay? This is the reality. The reality moving charges are moving this way. And now I'm gonna assume, this is my choice here. I'm gonna assume the current is moving this way, okay? So because these positive charges and the direction I selected here is similar to this direction, so in this case, the current is positive, okay? However, if I select the current this way, okay, and actually the positive charges are moving this way, in this case, when you do calculation, for example, you will find that current is negative. So when you find the current is negative, it means the direction you selected was not true. It has to be the other way. You understand what I'm saying? So you can select any direction. It doesn't matter. Okay. So let me clarify, because this is something we're going to do later in this course. So here, usually what I want to say is that I may not worry about the direction. So for example, I'm going to say the current is this way, and then I will do the calculation. If I find the current is positive, okay, so my selection was right. If I find the current is negative, so that means it should not be this way, it has to be this way, okay? So that's why we should not worry much about the direction. Anyway, so however, we are going to do some changes here in case if the charge is negative. If the charge is negative, okay. Remember, the I is actually charge over time. I charge over time. So in case of charge is positive, okay. So and you select the same direction, you get positive current. But here, look here, because the charge here is electronegative, okay. So and I selected the correct direction, I has to be negative. You got what I'm saying? Why? Because I is actually charge over time, and the charge is negative. Here the charge is positive. So that means if it is electrons moving, okay, and I find I is negative, that means that the direction I selected is correct, okay. Anyway, I think most of the time we'll take this case, but anyway, so here electrons are moving this way, okay. So again, I just don't want to confuse you. You can tell from this equation, the current is a charge over time. So this charge, it has a sign. It can be positive or it can be negative, okay. In case of protons, it's positive, or in case of electrons, it's negative. So here in this case, electrons, so it is negative, okay. So, and because here I selected the wrong direction, the direction of the current is different from this one. This is negative, and this negative, in this case, I'm going to end up with a positive I. So let's make it simple, because I know it's a little bit confusing. So make it simple. If the charges are positive, okay, and I assume the direction of I this way, and then I find I is positive, that means the direction is correct. I selected correct direction. If I is negative, that means the current should not be this way. It's supposed to be this way. Here in case of negative, okay, if you select the correct direction, it should be negative. Otherwise, it is you get a positive one. That means if it is positive one, that means the direction is different from this direction. Anyway, so after that, here I told you current or Q charge, actually they can be function of time, okay. So for example, I give you some examples here. For example, here I, the current, can be function of time this way. It can be sine wave, as you see here. For example, I equal I. This I here is actually the magnitude, as you know, sine omega t. Okay, so here I omega t. So it can be function of time. It can be this way. Okay, or it can be exponential this way. So it's a function of time. It can take any function, but for sure this one is very popular. This one also is very popular, and so on. Or it can be constant time. So here what this means, if it's a relation with the time, that means I is constant here. Okay, constant. I does not fix it. That in this case we call it DC, or direct current. Direct current, DC. Okay. Let's now have some examples to understand how this example should focus on these two formulas I did before. Given Q, how can you calculate I? Or given I, how can you calculate Q in different ways? So here, let's start with the first question here. The following figure shows a uniform. Very important, the word uniform here. Very important. Uniform means constant move of electrons from left to right. So the electrons are moving this way from left to right, okay? And so here I'm asking you, and then assume a total of 12.48 times 10 to the power 18 electrons cross the area A in 5 seconds. Okay, so this is given to you, and it's constant. So every 5 seconds, this amount of electrons are moving this way, okay? So find the current I. Find the current I. So this is all the information I have. There is one information missing here, which is in case of uniform. Okay, so you don't do differentiation in case of uniform. It's not missing, but it just here this one if Q is a function of time, but here Q is constant. Okay, so here I is actually amount a change of Q over a change of time. Is that okay? but here it is uniform motion, okay? So delta, and it's given in the question here, it is actually 12.48 times 10 to the power 18 electrons moving every 5 seconds. It's constant, it's uniform, okay? So it's very simple. So if you want to calculate the current, so the current here is this amount here, okay, divided by 5. That's it. However, this one here, a number of electrons, it's not in column. This is not Q, okay? This is not Q. This is number of electrons. That's why I have to multiply this number by the charge of one electron, which is this one here, okay? So the first thing I have to do here is to calculate Q. So Q here is actually the number of electrons times the charge of one electron this way. So after I do the multiplication, I'm going to get -2 here, -2 column. This is not exponent, this is column, okay? So here I got -2 column. Again, this is negative because this is the charge here is electron. If I change the same example and I tell you it is proton, so this would be positive because in proton it is just positive, okay? And so here we have constant change. So every 5 seconds, the change here in Q is 2 every 5 seconds. So that's why when you calculate I here, I is actually change in Q divided by change in T, and this is constant, okay? So it should be -2 divided by 5, should be -0.4 ampere, okay? Because the unit of current is ampere, okay? Again, I didn't do differentiation here because he told me uniform, okay? Uniform change. So every 5 seconds, this is a change here, a total cross every 5 seconds. That means the amount of charge here at the right here is increasing by this amount every 5 seconds, and this is constant, okay? The only trick we have here is I give you the number of electrons. I didn't give you column or I didn't give you in column. That's why you need to get Q. You need to calculate Q. To calculate Q here, I have to multiply the number of electrons by the charge of one electron to be in column. Okay. The other thing you can see here, it is in negative. Okay, it is in negative here because you know, I can make it positive easily. You know how I can make the current this way, but here I know it's electron. I know it's moving this way. Okay, and I assume the current here is the same direction like this one here. That's why current here is going to be negative. If it is protons, the current would be positive here. Okay. Let's see another example here. Just give me 1 second. Yeah. So let's see another example here. So here in this example, I have here, I give you Q as a function of T. I give you 3 cases. The first case when Q of T is equal to T. Okay. This is a Q function of time. I give you Q of T 2 sine 10T. Okay. And then I give you Q of T like this figure. This is the third case. So we have 3 cases here. And then I'm asking you to calculate the current. So giving Q. So that means I will depend on this one here. Okay. So giving Q, I want to get the current. Okay. I just in every slide I repeat this one because this is the information I have, but actually we don't need this one because I'm going to use this part if I have I and I want to get Q, but this time I have Q and I want to get I. Okay, so let's start with the first one. This is very simple. It's like you can have these examples in calculus, okay, because this is like a direct application to integration and the differentiation. So here given Q of T equal to T, okay, in order to get I, just I'm going to differentiate. I'm going to differentiate this one. So here Q of T equal to T, I is actually d dt Q of T. Okay, so in this case I'm going to differentiate. You know, when I differentiate to T is actually equal to. Okay, I want to make sure. I'm not sure if you have some weakness in we don't use very heavy calculus so far, but just in case if you have any weakness or you want to remember you need to refresh your mind or read again in calculus. But in calculus, if you have a constant like 2, this constant, we can get it out. And when you differentiate t, the result is 1. That's why the result here is 2. Okay. And that's it. So that means if you see here, this is q of t. Q of t is increasing this way. Okay. But I is actually constant this way. Okay. I is constant. The current here is constant. But q is linear, as you see here. Okay. Let's see the second case. In the second case, I'm telling you q of t is actually 2 sine 10t. 2 sine 10t. Again, this is a very simple example. It's like a calculus problem. All what you have to do, just the relation between I and q is just differentiation. So here, I'm going to differentiate this one. And to do this one, all what you have to do, number 1, this is a constant, you can get it out. This number 1. Number 2, the differentiation of sine is cosine. Okay, so we have these two constant here. I'm going to get it out. Sine should be cosine, as we see here. Number 3, you have to multiply by the differentiation of what is inside here, 10t. The differentiation of 10t is 10. So I'm going to multiply by 10. Okay, I'm going to say it again here, guys. It should be very simple, but I know maybe some of you have weakness somehow or want to make some refreshment. So again, the way we do this differentiation is, number 1, we have a constant 2. So I'm going to get it out. This number 1. Okay. Number 2, sine should be cosine. Yeah, this way. Number 3 has to be times the differentiation of what is inside here. 10t, the differentiation is 10t is actually equal to 10. Similar what we did here, the differentiation of 2t is actually equal to 2. That's it. So when you multiply it, this is the current. It should be this way. Okay. So that means, as you see in the figure here, if the charge q of t is actually, if the charge is sine, as we see this way, we are gonna get cosine here, which makes sense simply because just a differentiation, the relation between them, q and I, is just a differentiation. So if this is the q is this way, I has to be this way. If it is sine, this one becomes cosine. If this one cosine, this one becomes sine. Differentiation. Okay. So let's now see the third case here. The third case we have here. Here in this one here, you can see this one is increasing, and then this part is constant, and this part is actually decreasing this way. So we need. So number 1, you have to get equation for each part. So I'm going to divide it between 0 and 2, and then from 2 to 4, and then from 4 to 5. And then I'm going to do differentiation for each part. So let's do the first part here. You know this is a linear equation. Okay. You know because it's passing by 0, there is no intercept to y axis. So actually, this is y equal slope times t. Okay. Should be plus c, the intercept, because but here in this case, because it is 0, there is no intercept. So the equation here is actually, this equation from 0 to 2 is actually q of t equal slope times t. How can you get the slope? The slope is a change in y, which is this part here, 10, it changes 10 in 2, right? So here, you know, y2 minus y1 divided by x2 minus x1, or so here, assume this is y2 minus y1 divided by x2 minus x1. Okay. So if you do that, the slope becomes 5. That means the equation here is actually 5t. Okay. The equation for this part. The equation for this part is very obvious, very easy, just constant 10. Constant 10. Okay. So let's look at this part here. Okay, for this part, this one has it's like a straight line equation. In a straight line equation, y, which is q in this case, equals slope times t plus intercept b. Okay, let's start first with how can you get the slope? How can you get the slope here? To get the slope is actually, again, as I told you, all what I need only 2 points. Okay, so for example, if I take this point here, this point x is 4, y is 10. This point x is 0, x is 5, y is 0. Okay, and then you can use the formula y2 minus y1 divided by x2 minus x1. Okay, so that's exactly what I did. Okay, or so here, for example, here, what we did is 0 minus 10, 0 minus 10 divided by 5 minus 4. Okay, so which is minus 10 slope. There is something you should know. If the slope is this way, pointing at the first quarter and the third quarter, so the slope has to be positive. And if it is this way, okay, pointing at the second quarter and the fourth quarter, the slope has to be negative. Okay, I'm saying that because if you make a mistake, you can correct, you can know this wrong, right? So because before I do calculation, I know the slope here is positive, I know that slope here is negative. There is for sure another way to know. As x increases, y increases. So if I'm here and then I'm here, you can see increase. That means it's positive slope. But here, as you increase, as x increases, y decreases. Okay, so that's why the slope here is negative. Okay, that's how you can calculate the slope. So now the equation is q is equal to negative 10 t plus b. Okay, so now I want to calculate b. To calculate b, all what you have to do, you have 2 points here. Okay, you can plug in using any one of these 2 points. So I have this point here, which is x4, y is 10. You have this one here, which is x is 5, y is 0. You can just plug in using any one of them. Here in this example, I selected 5 and 0. So here I put here in this equation 0, y is 0, x is 5, and then I can get b. So after I get b, I found it's 50. So now I have the complete equation. So now the first thing you have to do here, I need to get the equations here. Okay, this is the first part I did here. So now here in this part from 0 to 2, we found that it is 5t. Okay, the equation here. Here from 2 to 4, we found it is 10, constant 10. And then from 4 to 5, we found it. This is the equation here. Okay, so this is q. Yeah, so here we spent some time just to calculate q because q is not given to me. So it's different from the previous cases. So in the previous cases here, I give you q here, I give you q here, but here I didn't give you q, but I give you a plot. Using this plot, you can calculate q. After you calculate q, so now it becomes easy. All what you have to do, you have to do differentiation. You have to differentiate here to calculate q of t. Okay, so here, yeah, so this is q of t here, and this is the relation we have. Okay, so here when you differentiate 5t, it is 5. When you differentiate a constant value, it is 0. Okay, this is a calculus. Differentiation of a constant value is 0. When I differentiate this one, so this part is going to give me minus 10, but this part is going to give me 0. Okay, you know, when I differentiate two items added together, so I can differentiate this one plus differentiation of this one. This one is 0 because it's constant. This one is negative 10. Okay, and that's it. So this is the current here. Okay. There is something you can notice here. Here the current is 0 in this area. So from here to here, the current was 0, which makes sense. You know why? Why the current here is 0? Because there is no change in Q. So the amount of Q here was the same. So that means it's like you can think always for current, you can think about pipe of water, okay, of liquid or water. Okay, so if the amount of water here is the same, that means there is no flow. There is no flow. Okay, that means there is no current. Just I wanna explain to you what this means. Okay, here the flow was 5 every 1. So every 1 second it increased by 5. Okay, this one decreased by 10. Anyway, let's have another. I think we have 2 more examples here. Yeah, but this time in this example we are gonna it's gonna be, so in the first 2 example I give you q and I ask you to calculate I. So that's why we used to see this formula. Now I'm going to do the opposite. So now we're going to do the integration, this part here. So I'm going to give you I and ask you to give me q. Okay, so yeah, let's look at this example here. So in this example, yeah, I give you the current. So as you see here, the current is constant this way. and then I ask you, give me, if starting from time 0, okay, and then it's constant this way, and then I ask you to calculate Q. What's Q? Is that okay? So again, the formula we have here, the formula we have here, this formula we have here, okay, I can calculate it this way, or I can calculate it this way, assuming T0 here is 0 at time 0, okay. So so here, the way you can, for example, I'm going to use this formula here, or let's see here. So for when t less than 0, okay, this part here, because you have to look from negative infinity to t. That's what you have to keep in mind, from negative infinity to t. Okay, so I'm going to divide it from negative infinity to 0, and then from 0 to t. T is any time here. Okay, so yeah, so it is from t is less than 0, or in other words, from negative infinity to 0, or the second part here is t is greater than or equal 0. This part here. Okay, so let's start with this one. When t is less than 0, okay. It's very obvious here in the figure, I is 0. There is no flow. Okay, so that means because I is 0 here in this part, Q is 0. So the initial value here we have Q at this point here is a charge was 0, because there was no current before it. Because there is no flow, there is no current, right, before it. Okay, so at this initial value here is actually Q of 0 is 0. Okay, now let's look at this part here. In this part here, I is constant equal t. And this is the formula we're going to use. Q of t is equal Q of 0, which is the initial value. I'm using this formula here, where t of 0 is actually at t0 is time 0. Okay, so here at Q of 0 is at time 0. So this one is 0. Okay, because there was no current before it, plus the integration from 0 to t, okay, 10 dt. Okay, as you know in integration, when you integrate a constant value, should be 10t. Okay, which is actually the opposite. I don't know how good you are, or it's not about how good. I'm sure you took calculus. I'm sure you did well, but sometimes you forget. Okay, so I'm assuming you remember. So, but I'm not sure if this assumption is true or not. But that's why I'm trying to just some simple stuff to just explain them. So here, you know, in calculus, it is a 10 is constant value. I can take it out, so it should be t, and the result here is t. Okay, when you differentiate dt, it is t, and then you have the limit here. The limit is 0 and t, and then after that, when you plug in, you plug t here, and then you plug minus 0 here. That's what I did. So this one and then this one. Okay, so the result of this one is actually 10t. So the conclusion here, the amount of a charge when t less than 0 is actually 0, but when t is greater than 0, it's actually 10t. Okay, that's why if I draw a figure here, it should be look like something like that. Okay, and let's make it very simple. What if I do the opposite? So given, just to make sure this is true. Okay, so given this Q, if you differentiate it, you will get this one. Okay, if you integrate this one, you will get this one. That's why this one should be true. Okay, because if you differentiate it, you will get here this one. Let's see the next example here. Okay, so let's see the next example here. Here I give you the current. The current was this way here. Okay, so how this case is different from the previous case? Okay, this is a very important thing. Looks the same. No, they are not the same. Why? Because here I divide it into two parts. This is one part here, okay, and then from here to infinity is another part. Okay, I divided two parts. Here we have three parts. So this is the main difference. Okay, we have one part here, and then we have one part here, and then we have another part here. Okay, so I'm going to divide into three parts. Okay, and then I'm going to calculate the amount of Q in these three parts. Okay, so let's see here. Let's start in the very beginning here, from minus infinity to 0, or when t less than 0. Okay, which is from minus infinity to 0. Okay, so in this case, current is 0. Okay, so if you make a differentiation between minus infinity to t, and t is actually from here in this area, and always the current was 0, so actually Q of t is 0. Okay, so in any part here, don't be confused when I say Q of t. Yes, Q of t, because t is here in this area. So for any value of t here, I'm gonna get 0, because always the current was 0. Okay, that means the initial value here is 0. The initial value here is actually Q is 0. Okay, and that's what I'm gonna do here. So if you look at the initial value here, when I look at this part here, from 0 to 2, from 0 to 2, so actually here, t0 here is 0. Okay, and this initial part I already calculated it was 0. So here I'm gonna say this one here from minus infinity to t, and t here actually between 0 and 2. Okay, the first part here, we already calculated it, which is actually the qt of 0. Okay, which is 0. Okay, and now in this part here is actually integration from 0 to t. Okay, but t is actually between 0 and 2. So any value here between 0 and 2 is t, any value. So this formula is true for any value here in this range from 0 to 2. So once you calculate this one, you have here 10t. Okay, and then just integration, and then you can plug in. So it's a limit. So this one minus this one this way. So the result is 10t. So the Q value here is 10t. Okay, and t is a value between 0 and 2. Okay, here it was 0 because there was no current here. Okay, look at the common trick, and this is the important part. Okay, or the tricky part. Okay, what about this part here? There is no current. So what is Q? Without any calculation, just think about it. By intuition, what's Q? Okay, don't tell me Q is 0, because Q is not the flow. The flow is current. The flow is 0, but I already gained some Q here. Okay, Q is the total, how much I have here. In the very beginning until 0, this one was empty until 0. Here in this part, because of this current, I started to gain Q here, Q some value. Okay, and then the last value here, this value will be the same here, because there is no more charges coming. Okay, so the last charge I had here, okay, or the charges accumulated during this time is actually what will be here, but initially it was 0. Okay, and that's exactly what. So here at this moment here, just this is without calculation, just by intuition, by thinking about it. So here, this is the formula for this part from here to here, from 0 until 2. So if t is 2, so this one should be 20. Okay, that means in this part here, Q was 20. So because we already gained some charges from this part here. So okay, so but I'm gonna use a calculation. It was 20, but I figured it out without any calculation. Okay, so if you see here, initially there was no charge. Okay, this is the first part we calculated, and now the formula here, it was a straight line. It was 10t here. Okay, so that's why it was increasing charge, because we had current, we had flow, so flow of charges. So now current, but once we come here, it's not 0, because we already have some value here, so it's going to be constant. Okay, so we already got some value here. Okay. What is 0 is the current, because the current is the new ones, new charges. Okay, the flow, but the existing ones is already here constant here, the last one, which is 20. But anyway, if you want to do calculation, I will do calculation here. So here in this part, okay, I'm going to use this formula here, where U of t0 is starting from 2, and then this one from 2 to t, and t can be any value here. Okay, So here, and Q of 2, T0 here, which is 2, is actually, I can calculate it from this equation by 20, okay? And in this part, it becomes 0. So that's what I did here. So if you see what I did here, for some reason, or what we did here, we calculated it again from the very beginning, from minus infinity to T. And then I'm going to split it into 3 parts, from minus infinity to 0, then from 0 to 2, and then from 2 to infinity. 3 parts here, this way, okay? And the first part was 0, okay? The second part here was I of t was constant 10, okay? From 0 until 2, okay? Anyway, again, this part you can, for sure you can do the calculations, but by intuition, you need to verify your, the intuition can be used to verify your answers. But anyway, now let's look at the last part here, which is from 2 until t, 0. So this part is 0, this part is 0. The result will be constant is 20. Okay, constant. And this is the result, final result. So from t less than 0, okay, Q is 0. For t between 0 and 2, Q is 10t, okay. And then after that, 2 and more is going to be constant this one. Any questions? Okay. We started at 4:30. Yeah, we can take one more thing here. Okay, so I want to make, let me go back just, I want to know, because I will spend much time on this one. So again, the purpose of this chapter is to define and to define Q charges, current, relation between them. Now I'm going to move to voltage, power, and energy. Okay, these are variables we use in circuits. Okay, you need to understand them. You need to understand the relation between them, as I'm explaining now. So now I'm going to come to energy and work. Maybe the funny part here is this is like physics. So this is the way we define work in any application in physics, not only here in electrical circuit. So now to understand what energy means, we need to start with work. What work means, okay? So in physics, this is how we define work in physics. If we have an object, if you have a body or an object this way, and then you apply a force, and after you apply a force, you were able to move. You were able to move this object distance L, as we see here. If you do that, in this case, we did a work. We did a work, or the work performed by the force. The force performed a work on the object, and we used to define the work this way: F times L. Okay. So this is like a definition. This is from physics. Okay. So in physics, there is here I wanna define energy. Okay. Here, energy here, I mean electrical energy for sure. But in order to understand energy, we need first to start with work. Okay. So work means F times L. Okay. The force needed to move object L, distance L. Okay. So here energy is very related to work, because energy is actually a quantity that represents the ability to do the work. That's why energy and work has the same unit. Okay. So energy is a quantity that represents the ability to do work. Okay. The higher energy, that means you can do more work. That's very simple. Okay. So the unit of energy and work is the same. So now let's get what is the unit of energy or work. Okay. So work, as I told you, it is F force times L. The force I apply to object to move it L, distance L. Okay. You know, so that means the unit of work is actually Newton. If the unit of force is Newton times meter. Newton times meter. Okay, so this is the unit of work or energy, because they have the same unit. Okay, so actually Newton times meter, we call it joule. Okay, so this is the unit. This is the unit of energy. It's joule. Okay. So 1 joule or 1 Newton times meter. Newton times meter means joule, okay? But for sure, usually we don't use it this way. We use 1 joule, but the joule means Newton times meter, okay? So 1 joule means the work performed by 1 Newton force moving an object 1 meter, okay? So here, if this is 1, so this is 1 and this is 1. So here, if I have 1 Newton to move an object 1 meter, this is 1 joule. Okay. Anyway, so the work performed by this is 1 joule. Anyway, so now now you got some idea about we know the unit of energy. Okay, and we defined energy in terms of work, the ability to do work. Okay. Now I want to we want to focus more on electricity. This is like a general for any phenomena in physics. So anyway, so here when we talk about energy, we mean electrical energy here, because you have a battery. This battery is providing electrical energy. Okay, so for example, if you have a battery this way and you have a bulb or a lamp this way, okay, and then the switch is open. If the switch is open, there is no current. Current is not gonna flow. There is no current, and by this way, there is no light here. Okay. However, if you connect the switch this way, current is gonna flow this way, and actually, what we are doing right now is we're transferring energy from the battery to the lamp here. Okay, so that's why you can, and this energy, the chemical energy here, we transfer it into the in terms of electrical energy to generate light and heat here. Okay, let us close the switch. The current will flow. Actually, here we charge Q moves from A to B. Yeah, so here's the charge. So charges start to move here because of chemical reaction here. Okay, this energy is called electrical energy. Okay, electrical energy. The electrical energy is produced by the battery. Okay, and it is in this case it produced by chemical process. Okay, and actually what we did, we actually we converted the electrical energy. We converted it into here in this case it can be light and heat. If I put here a motor, so I'm gonna convert it into motion or mechanical motion. Okay. What I want to tell you here, we can generate, as I said before, we can generate electricity either by by using batteries. Now we have electrical vehicles here. It can generate electricity by chemical reaction. Okay, chemical energy, convert chemical energy to electrical energy. But also we have in practice, most of electrical energy is obtained through mechanical energy. This is generator. If you have a generator, so we can generate electricity by using mechanical. Okay, I think that's enough for today. Okay, thanks so much.